Hi, my name is Luisa Fiedler, and welcome to the talk of our paper Self-Similarity Beats Motor Control in Augmented Reality Body Weight Perception. My co-authors are Botsch, Carolin, Wienrich, and Marc, Erich, Latoschik. We are from the Psychology of Intelligent Interactive Systems and Human-Computer Interaction Group from the University of Würzburg and from the Computer Graphics Group from the University of Dortmund. A negative or distorted perception of our own physical body can affect our mental well-being and often manifests in negative consequences such as body dissatisfaction, body shape concerns, diminished self-esteem, and in severe cases the development of body-related disorders. At the moment, regular treatment often leads to high relapse rates, so we need to explore alternative treatment options. Recent research showed that virtual humans in virtual reality can be powerful tools for addressing body misperceptions. But augmented reality offers its distinct advantages in medical settings. So it allows patients to stay within familiar environments and maintain direct interactions with therapists, which is crucial for fostering a therapeutic alliance. But how do we perceive bodies? Previous research found two main factors that shape how people perceive virtual humans in AR and VR systems. To differentiate between VR and AR research on the next slides, the AR studies are underlined. First, users can motor control the virtual human's movements through visomotor synchrony, allowing it to function as their own virtual body. So, a use case is feasible where users can observe a motor control virtual human through a virtual mirror, as you can see here in this little video. The different use case, a non-motor control use case, could be observing a non-controlled autonomous moving virtual human through a door frame in another room. Secondly, virtual humans can be self-similar in their texture to the user to match the user visually. So users can observe, for example, a virtual human with self-similar texture. The other use case, a non-self-similar use case, would be observing a gender-matched virtual human with an unfamiliar generic texture. Maybe it's a bit more visible on this picture here. Okay. So, previous research showed that both factors evoke or intensify the sense of embodiment and self-identification towards the virtual human in VR and also in AR systems. But are these factors also influencing virtual body weight perception? Yes, at least in VR systems. Prior VR research showed an influence of motor control and self-similarity on body weight perception of virtual humans. But what about AR settings? While body weight perception of virtual humans has been widely studied in VR systems, research in AR remains limited. In fact, only 4 studies have explicitly examined this topic in AR. Since AR provides a different level of immersion, it may affect how we perceive the body weight of virtual humans. This raises the question of whether the same factors influence body perception in both AR and VR systems. Let's go a little more into detail about that. Why could perception of virtual humans differ in AR and VR? As I said, the level of immersion differs between AR and VR because AR blends real and virtual elements. This may affect how we perceive virtual humans in AR, potentially leading to a less coherent experience as suggested by theoretical work. First, Scarbus et al. Expanded Milgram's reality-virtual reality continuum, providing a framework for mixed, augmented, and virtual reality. They point out that in VR, coherence is mainly internal. Virtual objects must only interact predictably with each other and the user. In AR, on the other side, coherence also depends on external factors, meaning virtual objects must interact predictably with real objects as well. Additionally, Latoschik and Wienrich's congruence and plausibility model suggests that AR introduces virtual inconsistencies due to differences in rendering, which may impact how we perceive virtual humans. Based on this, we have the following research questions. First, what role do motor control and self-similarity play in virtual body weight perception in augmented reality systems? And second, does virtual human body weight perception differ in AR and VR systems? To investigate that, we conducted a study following a 2x2 mixed design with 60 participants. As between factor, we manipulated the motor control between participant and virtual human. In the motor control condition, the participants either observed a controlled virtual human, which mimicked their movements, In the no motor control condition, they observed a non-controlled virtual human which did different movements, as you have seen both in the video at the beginning of my talk. Motor control and no motor control are marked with those little signs, as you can see here and here on the following slides. As with N-factor, we manipulated the self-similarity of the virtual human. In the self-similar condition, the participants observed a self-similar textured virtual human, while in the non-self-similar condition, they observed a gender-matched generic textured virtual human. Self-similarity and non-self-similarity are marked with those little signs in the following slides. As dependent variables, we measured the sense of embodiment, self-identification, and body weight perception. Furthermore, to explore body weight, the virtual humans we use for our study are modifiable in body weight, as you will see in a few seconds in a short video. The procedure of our study was as followed. First, we created a self-similar virtual human from each participant by using the body scanner in our lab. While the avatar generation pipeline ran, participants answered different pre-questionnaires. Then, the first of two similar XR exposures started. The participants experienced both exposures either while observing a controlled virtual human in the motor control condition or while observing a non-controlled virtual human in the non-motor control condition. In a counterbalanced manner, the participants experienced a self-similar virtual human and a no self-similar virtual human, one in each exposure. In the AR exposure, the participants performed 5 body movement tasks, where the controlled virtual human copied their movements, or where the non-controlled virtual human did different movements. Then, the first body weight perception task followed. This was an estimation task, where the participants estimated the body weight of the virtual human 9 times with modified body weight in a range from -20 to +20% of their own body weight. After that, the participants performed the second body weight perception task. This was a modification task where the participants modified the virtual human's body weight to their own current body weight. And here you can also see the body weight modifier virtual humans quite good. After finishing the tasks, participants answered post-exposure questionnaires and were interviewed. Then the second AR exposure followed. Okay, let's have a look at our results. What was the role of motor control and self-similarity on body weight perception in AR settings? So, here you can see the plot of the results of the estimation task. You can see the misestimation of the virtual human's body weight on the y-axis, and on the x-axis you can see the non-self-similarity and the self-similarity condition. The symbols, the triangle and the circle, are marking the motor control and no motor control conditions. For the estimation task, we found a significant influence of the self-similarity between participant and virtual human. The body weight of self-similar virtual humans was estimated more accurately than the body weight of generic virtual humans. For the modification task, the participants were asked to modify the virtual human's body weight to their current body weight. Here we found the same effect, a significant influence of the self-similarity between participant and virtual human. The body weight of self-similar virtual humans was estimated more accurately than the body weight of generic virtual humans. Overall, our results showed that the crucial role of self-similarity in shaping the accuracy of virtual human body weight estimation, whereas the influence of controlling the virtual human's movements appears minor. Okay, let's go back to our question. Does virtual human body weight perception differ in AR and VR systems? Our study highlights the key role of self-similarity in the accuracy of virtual human body weight estimation, while the influence of motor control appears to be minor. In contrast, a VR study by Fiedler et al. Using the same design showed that in VR the influence of motor control is more pronounced. This weaker effect of motor control is consistent with the weaker impact of motor control on sense of embodiment compared to the VR study of Fiedler et al. Likely due to the augmented reality setting where the user's real body remains visible alongside the virtual one. Since the real body has no motion to photon latency, any delay between real and virtual movements during the interactions with a controlled virtual human becomes more noticeable. And these mismatches are more pronounced in AR than in VR settings and may reduce the external coherence, thereby weakening the effects of motor control on the sense of embodiment and consequently on body weight perception. Overall, our study highlights the need for further research to better understand the unique effects of AR systems on body weight perception, particularly regarding external coherence with the real environment. Thank you for your attention.